All right, so this section is examples of subspaces. So all of this is basically what are different types of subspaces we can actually automatically define, and if we could find it, it's automatically a subspace of the Rn value. Okay, so the first one is linear independency. So given vectors v1 through vr are in vectors of vn. Okay, so then a set W consists of all linear combinations of v1 to vr is a subspace of Rn. So if we can prove that this is a linear combination, or this set W is a linear combination, therefore it's automatically subspace of Rn. Okay, and we'll talk about that a little bit more as well. But for now, what does this really mean going forward? Okay, so if S is these vectors and it's a subset of Rn, so kind of this situation here, then by the last theorem we say that S containing all linear combinations, so all forms of linear combination, is a subspace of Rn. Okay, the reason why this is so special, right? I just redid the theorem, is because this is called a subspace spanned by S, and it's denoted by SPS. So the span is SP of S. So it's a subspace span of S. So that's why this is so important, because it has its very own special name. And a lot of these subspaces do actually have its own special name because they're very special in that way. Okay? So again, whenever you see SPS, that means it's all linear combinations of these vectors. Again, is automatically a subspace. Okay. Now, a quick reminder what represents be a linear combination. So given any vectors is v1 through vr, it's a linear combination of another vector itself, right? The arbitrary one. Now, in most cases, all we need to do is find the span, and then it's pretty much it. But you'll see how we do that later on as well. But for now, it's just a simple little example here. So let u, v be vectors in R3. Okay. So we want to determine the span of uv. So in other words, we want to find the subspace bounded by these two vectors here. Okay, so if we follow this linear independency portion here, so we have vector y is equal to a1, I'll call u, this is the first one, u plus a2v, right? If we follow this template here, those are my vectors there. Okay, so now what I want to do is break it apart. So the component of vector y, y1 is equal to 2 a1 plus 0 a2. y2 is equal to 1 a1 plus 1 a2. And then finally a3 is equal to 0 a1 plus 2 a2. Okay, so now what we want to do is, because we want to find a linear combination, well, we got to put it into matrix format. So where these are what we're looking for, the y1, y2, and y3, and our coefficients, so a1 and a2, will be here instead of x1 and x2. So in this case, we'll have 2, 1, 0, 0, 1, and 2, and we're looking for y1, y2, and y3. All right, so this is pretty much already done, so we'll only just multiply this row by times 2 and just add it to the top row, and we'll eventually get this. And then divide this by 2. Well, simplifying everything as much as possible. All right, so now what does this give us? So remember, we want linear combination, right? So we need an actual solution. So this says it's consistent, or we actually have a solution if this equals 0. Because if it doesn't equal 0, then it doesn't make sense, right? No, there's nothing that can be, y2 cannot equal some number when it's 0 times it, right? All arbitrary values. So solving for this, all we want to do is get rid of the fraction, so I'll multiply everything by 2. So we'll just have y3 plus y2 plus 2y1 equals 0. Okay. So our span of vector u and v, squiggly here, squiggly, is the vectors y, where y1 is this, such that this is true. So we get a linear combination if this is true. Okay. And that's how we find the span. Remembering span is the linear combination of it, so all we have to do is solve for it and see when is it actually having a unique solution. And we have a unique solution when it's literally this equals 0 no matter what. Okay. So interesting concept. We'll come back to the span a little later on as well. But the next type of subspace is called the null space or the kernel. Many people actually use both depending on where you go. So let A be an n by n matrix. So the null space or the kernel of A, denoted as n parentheses A, is a set of vectors in Rn defined to be this, where I can find any vector, and when I multiply by the matrix A, I get 0. So remember, it's a vector, so our arbitrary x value vector is n by 1 matrix. This x1 all the way to xn. Right, so this multiplication would be a times x, right? So that's why this is an n by n, and this is an n by 1 matrix. So we get an n by 1 matrix, respectively. Okay. So how does this apply? So given matrix A and x equaling that, show that vector x is in the null of A. Okay. So remember, by definition of what the null space is any vector that's such that if I multiply them, I get 0. So all we have to do is multiply and see, do we actually get 0 or not? Okay. So we have 1, 2, negative 1, negative 2, times 2, negative 1. Okay. So it's just vector matrix multiplication, so this by this. So 1 times 2 is 2, plus this times this is negative 2. Okay. Next one. So this by this is negative 2, plus this times this is positive 2. So we get 0, 0. So that is contained in the null of A. So it does actually work. Okay. So again, if we find another vector, we have to show is it in there or not by just doing the same processes. All right. Interesting theorem here. If A is a n by n matrix, then the null space or the kernel is a subspace of Rn. So now we start into actually subspaces, right? So here we're already told by this theorem that the subspace, the span of the subspace is automatically a subspace, right? The span of S is automatically it. Here we just define what the null kernel is, and now we're going to, and this theorem says it actually is a subspace. But again, like everything else, we got to prove it actually does work. So first off, let's just write the definition of the null space. So given A is a m by n matrix, and I'm just going to rewrite the definition of the null space. Then the null of A is equal, again, just defined to be any vector x such that A times x equals 0. And if you want, you can keep going. I guess I'll just write the former definition of just that, where x is contained in Rn. Okay, so first thing, we'll say X is any vector that satisfies this. Okay. All right, so we have to show the three things to show it's actually subspace. So one, if this vector equals 0, so then matrix A times AX will be, well, 0. So that means that's contained in the null space. So check. And again, you could do point by point, right? So we go over here. So let A be some arbitrary vector. And it's just a bunch of zeros. And remember, when we do scalar multiplication, that times that plus that times that and so forth, the sum is just going to be 0 all the way down. So that's why this works. Okay. Now let's go to 2. So again, this is going to be a theme. So let AX equal 0, or sorry, let X equal 0 and vector Y equals 0. Okay. So therefore, AX plus AY. Okay. Well, we just proved that when you multiply these two, that gives you 0. Or more easily, if I just factor that out and just add the vectors themselves individually for a multiply, which I can do, I know if I add two vectors that are basically 0, that gives me times 0. Or if you want to define it, let C1 equal sum of those two, which is now the same process as above. So that is contained in the null. All right, and then the last one is scalar multiplication. So again, that be true, so then A times X is just going to be 0, right? It's a scalar times 0, it's still going to be 0. So matrix A times this process equals that vector there, A times the 0 vector, which goes to the theme, gives you 0, so that's in the null. So there you go. It is a subspace. All right, so now that we've shown it's actually a subspace, now we can use it. So we want to describe the null space of A for this 3 by 4 matrix. Okay? So in other words, we need to solve for this. We need to find a vector x1, x2, and x3 such that this actually works. So you could do it a couple ways. You're going to see in your book, they decide just to drop off the zeros. And what I mean by that is most of the time I will do this. However, in your book, they just leave it out and just start there. And then they do the row reduction here, because it doesn't matter what you multiply by zeros and add it, it's still going to be 0 at the very end, right? So this is basically a homogeneous equation. So that's the reason they can just drop the zeros and the result will give you the same thing anyways. But for consistency basis, I'll keep the zeros here. Okay? And now again, we just go straight to our row reduction portion here. And eventually, after a while, we end up getting this. And the key thing is, right, going forward, you are going to have to put it in complete row reduction form or Euclidean form before you actually solve for or you give the answers themselves. As you can see, it is in full row reduction form, right? Zeros, ones, and that's it. Okay, so from here, we have x1 plus 2, so it's easier, x1, x2, x3, and x4. So and x3 plus 3x4 equals 0. We have x2 plus x3 minus 2x4 equals 0. Okay. And since we talked about independency and dependent variables, if you notice, they have two vectors in common, or two components of the vector in common, 3 and 4. So we're going to solve for these. Meaning you just bring that to the other side. And there we go. We got our situation. So therefore x3 and x4 are arbitrary. Okay. So how do we write the null of A? Because we want to describe the null of A. So now we have to put it in actual notation purposes. So the null of A is any vector x such that this vector x is x1, x2, x3, and x4 such that these conditions hold. And x3, x4 are real numbers. However, there's an alternative way of doing this as well, if you don't like this format. And the alternative way is, get some more paper. Using its proper term, because technically this is a linear combination, so you can write it like this as well. There you go. Oh, where x3 and x4 are real numbers. So sorry, that's supposed to go right here. So two different ways to answer this question for the null space of A, or the kernel, depending on who you are and what book you're actually reading. Okay. All right, so let's keep a couple more examples of null spaces. Well, kind of null spaces, but for sure subspaces. Okay. Next definition we talk about is called a range of A. So let A be an n by n matrix. The range of A, denoted as R of A, is a set of vectors in Rm defined. Now here's a key thing, Rm. So notice, it's not Rn, it's Rm. It's the first component, so the number of rows. Okay? So again, so let A be an m by n matrix. The range of A, denoted as Rm, is a set of all vectors in Rm such that in all the vectors in the row that this is defined to be. So it's all vectors y equaling ax for some x in Rn. And that's the key thing. Notice is opposite. So there's a vector x in Rn this time in there. So if it's easier, you could think of like x and y as the range. So we're picking any vector in the range, so in the y component, and just vice versa going in the opposite. Okay, so a bit tricky when it comes to the range stuff itself. Okay, but the good thing is it's very similar to the null space itself. Okay? So the only difference between the range and the null space is, if you want to describe the range or describe the range of the null space vice versa, is, well, last time we set them equal to 0 because that was defined to be the null space. This time, however, we want to define all y values, or no, y vectors responsible for that. So all we're going to do is, instead of setting this equal to zeros like a homogeneous equation, we set them to its vectors, y1, y2, and y3, and then we solve for it there, and solve for the conditions we need for each individual case. Just like that. Okay. Now again, after a while of converting, so easy here I can show you. So I did y first row minus second row to get rid of this part, multiply this by 2 to cancel this out. And eventually, after a little bit of work, we break it down to this. Well, believe it or not, it's the same equation as before, right? So you just show the work again. But this time you have to get a little bit more because it doesn't equal 0. So I guess you have to start all over again. Okay, we get that. Okay, so again, we care about the bottom because that's what the big no-no is, right? So this is consistent if this equals 0. Okay. So I'll just solve for one of the variables since these are y2 and y3, so I'll just solve for y3 here. That would be dependent. Bringing everything over, so y3 equals that. So again, now we just define or describe what a range is. So the range of A, in this case, will be all y vectors such that y3 has this condition. And therefore y1 and y2 are real numbers. Or again, if you don't like this format, you can write it as this. So replace this part here with this. So it's linear independency portion. So, oh yeah. So y1. So y1, 0, and 3, and y2. There we go. So very similar to the kernel or the null space of A. The only difference is instead of these equal to 0, we set it equal to its components, and we solve what the condition will have to be. And now that we know how to do this, we can now state it's actually a subspace. So if A is an n by n matrix, and if R of A is the range of A, then the range of A is a subspace of Rm. Again, notice Rm, not Rn, Rm. Now, the last type of subspace we're going to talk about is a bit of a tricky one. It's kind of weird. It's kind of off. This is something called, well, before we get there, just talk about this. Something called the row space of a matrix. Okay. So if A is an n by n matrix, okay, then the columns of A, right, we talked about this earlier, the columns of A can be broken down into individual n by 1 matrices. Right, this is A1, A2, so forth down the line, right? Where it's the component. So if A is equal to so A1 would equal the first column of matrix A, and vice versa. So I guess you can put them as vectors, right? And then A2 would be the second columns all the way down. That's what these represent. Okay. Okay. So then the columns space, and that's a key thing. So the column space of A is a span, represents the span of A. Okay. And then we also have something called the rows of A, are vectors A1, A2, A3, all the way to AM. See? So these vectors go across instead, go this way. Okay. In Rn is called the row space. And again, it's denoted as the span of the vectors. So we have two different things. They have the column space and the row space. Okay. Column space is what we know so far. Row space might be a little different because it goes this way now. Okay. So now, why is that important? Okay. So last term of this portion is let A and be an n by n matrix, and suppose A is row equivalent to the m by n matrix B. Talk about that in a little bit. Then A and B have the same row space. Okay. So here's an example of what we're talking about. So if we have this matrix A, okay, and so if you want to do the row space, so the row space is these ways, right? So it's going to be A1 plus and A2. So A1 is going to be this part here, and A2 is going to be there. So the row space of A1 and A2 are those two itself. Okay. However, if I row reduce this as much as possible, I get this, okay, which is, we'll call that B in this definition, right? So we have A here and that matrix B there. So the row space here, and I have it on the other page, right here. So the row space of B is the spans of the vectors B1 and B2 such that these are also the same. Okay. So we get a span of B being B1, B2. And that's the key thing, is just two vectors. And that's what I said. Remember, if the numbers may not be the same. However, if we have the same number of vectors, and when it came to matrix equivalency, that's the same thing as saying they're identical or the same. And that's what this term says, is then because we have the same span, they are equal. Or so have the same row span. So 1, 2, 1, 2. Pretty interesting, right? When it comes to it. Now, that can get a little confusing how to actually do this, because now we get a very interesting type of situation here. Okay. So let's try this example out going forward. So let S be the vectors v1 through v4 be a subset of R3. Okay, but these are my vectors. We want to show there exists a T, so a subset T with vectors w1 and w2 consisting of two vectors in R3, okay, only two vectors, such that the span of my vectors above equals the span of these two vectors. So in other words, is we want to find the span of these four vectors and show that it actually only comprises of two vectors. Okay? And then eventually show that this is actually the same. Okay. Okay, and well, we got to find those two W's and see that they're actually the same. Okay. All right, so this is actually a lot of work, believe it or not. So the first thing is, well, we want to find the span, so going back to the very beginning, we have to solve for the system of equations. And I'll call this B1, B2, and B3 there. So we're talking about B1, so we have to solve for B variable anyways. Okay, so again, after a while of manipulations, right, so we've used this matrix C kind of before, we eventually get this. Okay. So same situation, right? The same type of vectors. So this is consistent. If that equals 0. All right, so that means B3, if I just want to solve for it, is equal to 7B1 minus 3B2. That's our situation. Okay? So our span of S, which is span of these vectors, is equal to any vector B such that vector B is equal to B1, B2, B3, where B3 is equal to the linear combination of these two. And again, that means B1 and B2 are real numbers. Or, again, you could write it as the linear combination. Oh, yeah. So we found our span. Our span is two vectors. Good. Okay. Now, so this is two vectors, and we have the vectors here. So now we have to show that this W1 and W2 is the span, or we have to show that we only get two vectors with this vector, and then they're exactly basically the same situation. All right, so to do so, to find T, we're going to use the last theorem. Okay. So the last theorem stated this. Not this one, but this one here. Well, kind of this theorem, but this situation. Okay. Something called using the row space and the column space. Okay. So we're going to do a transpose of our matrix, and then we'll work with that. Okay. So that way we could follow this process here. Okay. So A transpose, is where we're going to transpose this up. So now instead of being a 1, 2, 3, 3 by 4 matrix, now it's going to be a 4 by 3 matrix. Now we get this. And now we're just going to break this down. Okay? And again, we'll just slowly break it down. So again, Euclidean form, and this ends up being kind of interesting. Eventually, we get something like this. Okay. Now, this matrix is B transpose. Okay. So according to the last theorem, the span of this is equal to the span of that. Okay. So now what I'm going to do is retranspose it, or basically untranspose it. So we now get B. So this gives me 1, 0, 7, 0, 1, negative 3, like that. Okay. So T, which was the vectors W1 and W2, end up being, well, W1 is 1, 0, 7, and W2 is 0, 1, negative 3 from our B value. And if you notice, those are the same we just got above. So that means the span of S does actually equal the span of T. Check. So interesting, nice equation, or example of that, how to do from one to the other, and how to manipulate transposes and use the theorems to help you out when it comes to it. So this is a pretty tough one, especially whenever you want to deal with given two row reduction portions and show that the span equals the other span. But it's a bit of a long process to do so.